x direction. And how to find the E? How to find E? Usually, if I just give you a charge and I tell you charge is Q, okay, and using either Coulomb's law or Gauss's law, you can actually find what is the flux, what is the phi here, potential of flux, whatever. Let's say potential. You can find the potential outside, and from the potential, you find the potential dl or ds, d whatever. Differentiation of the potential, you find it. So from the Q, you find the phi. From the phi, you find the phi. This is the normal way of thinking, normal logic. So let's have a look at the solution. Usually people don't understand the solution. The first one is they are saying that let's ignore the right one. Let's just say we only have the left one carrying a charge of Q. Okay? Carrying a charge of Q. And at the distance of R is somewhere away from it. For example, from here, if this is the origin, R is somewhere outside. And at the distance of R, this is my potential, phi. And from the phi, actually, later it goes to find the E by using phi to find the differentiation. Okay? So this is the logic. But we need to understand where does this one come from. Do you recognize this formula? I don't assume so because it's not an ideal formula. It's from some calculation. So now our target is to find this one. When you have a charge, how do I know what is the potential at the certain place? If I know the charge. So basically, let's think about this guy. I have a wire. It carries a lot of positive charge, and let's say the charge is Q. Okay? And of course, it will give you the other direction also. Okay? You use E. And at some position R, if this is 0, this is my R. So what is the phi R here? This is my question. How to find it? Okay? And for this question, we need to refer to Gauss' law. Basically, Gauss' law is saying if you know this guy is Q, the flux, electric flux, will equal to Q over epsilon. And also it equals to the field times the area. Area in this case, if you need to say this is my charge, is the rod, and it has a lot of lines going out. If I'm using a cylinder to enclose it, okay, I use a cylinder to enclose this guy, put it inside, and the side area of the cylinder, that is the area A1. Because your field lines are all going outside this rod, they're all going puncturing through this cylinder, right? All going out of the side area. So the total area that has a flux, that's just call it A. Okay? And the A, actually, we can find out what is the A. Because this is a cylinder. The cylinder has a radius of R. It also has the height. Height happens to be the length of this rod. Let's just call it L. If we call it L. Why we call it L? Because in this case, they are calling it L. The length of the rod is L. So we have L, R. So in that case, the A is 2 pi R times L. Circumference times the height of the cylinder, that is the side area. Okay? And from here, I can find my E. The E will equal Q over 2 pi R L. Times epsilon. Okay? And our target is if you know the E. By the way, the E I can actually call it ER. Yes, it has the R here, right? So what is the flux? Sorry, what is the potential in order to know the potential now, if you have the field already, you can integrate the field and have the potential. But potential, we always say potential itself is meaningless because you need a reference. We always talk about the potential difference. Okay, we need a reference. So let's just say in this coordinate system, we choose another position. We will somewhere, maybe somewhere here. This is my reference. The reference has a radius of r naught. Okay, the reference. So the potential at phi r, potential at r is actually something like this. Phi r will equal to integration from r to r naught dr dr. Actually, nobody questioned me. I'm not always right. I left one thing. This one, we usually say integrated with E, you have phi. But this one, why it has the range from R to R naught? This is the integration. This integration will give you a potential difference between the R and R naught. What's the integration? What's the difference in potential? So actually, that is phi R minus phi R naught. So this one actually equals to phi R minus phi R naught. Phi R naught we suppose is the constant we know. So that is the reference potential. So in this case, when phi R equals to phi R naught minus equation R naught go over 2 pi epsilon L times 1 over R. Okay? And this one actually equals to phi R naught. Equation of 1 over R. We'll talk about that just now, log R, right? So minus Q over 2 pi epsilon L log and in this case, we have something here and we have something here. This guy, I suppose, is the constant. If you have a fixed charge there, this guy, phi r is the constant, I call it C. And then like that, I rewrite this equation and put it here. You can compare our conclusion here with this guy. This is how we have this guy. The C is the reference. Reference at no, the other is the other way, so I say. Okay? So far we are saying if we only have one loss, carrying the charge of Q with the reference at R naught. So another position R has this potential, where C is a reference. So in this case, this one is more complicated. The question is more complicated because you have two sources of the field. We're only talking about the positive one. This is the positive one. How about the negative one? Negative one is actually something similar. You only change the Q to minus Q, right? So the total potential will be the positive one plus the minus one plus the negative one, right? So this is why this part, what this part is going to say. Okay, let me give you more details. So if we have this one, let's say at somewhere, the total distance is d, right? By the way, so if at somewhere with the coordinate of x, okay, at x. So at x position, my field is given by this positive, this negative. The positive, this is negative. The positive one is giving me something like this. I call it phi 1. Phi 1 r equals to minus q 2 pi epsilon l log. What is my radius now? At x. The distance between the source and me is x. Okay, it's x. So ln x over plus c. The c I call it c1 because later we have another constant. This is my first potential given by the left one. I have another potential given by the right one. I call it phi 2. And in phi 2, the only difference is the q will be a negative charge. So q is a negative q. So I have a q over 2 pi epsilon L because it's negative, and my q is negative will cancel. And again, log. If this is x, what is the distance between my test point to the right? The total distance is d. Total distance is d. This is x. So on the right we have a d minus x. So we're talking about another distance. So log d minus x over plus c2. Okay. So in case someone were lost now, first we have this one. If you have a q, and now we know the distance. Let's say the distance is x from the left to the test point somewhere here. If this radius is x, the other radius to the right, that is d minus x. Basically, just keep subbing into this one. And because we both have some constant, we don't know whether they're the same, but let's just call it c1, c2. Adding these two up, you have this type. It applies to any position x between these two rows. Okay? So now we have the phi. Remember, if you have the phi, how are we going to find the e? Differentiation. d phi dx, or d phi d length, or d linear, whatever. In the field line, according to the field line, find the differentiation. So find the differentiation of this equation with respect to x. You will find this. I leave the conclusion to you, but let me just tell you. So if you add the phi 1, phi 2, phi 1, phi 2, and that here, and then you have this guy. From this guy to this guy, you find the d by x. All the way to something like this. So if you are looking at this equation, our E, the function of charge, epsilon L, x, and d. Okay, epsilon and L, pi is not the problem, it's constant. X is something you set, d is a constant. So basically you can say this field is a function of the position. Of course it's a function of position, it always is. But there is something we don't actually have. That is this one. This Q. We don't know what is Q, nobody ever tell Q. It's only that just now we said, hey, for a charge of Q we have something like this, right? For a rod with a charge of Q we have something like this, but we don't know Q. Okay? So from here we need to wait and find Q. What is a Q? If we know Q, submit to this one. We'll come back to option 2. Now let's move on. How do we actually find Q? There is something in this question that we never use. We make use of the D, we make use of the I, but we never look at this guy. They give you the U, the potential, voltage drop between these two rods. If we are saying this guy has positive Q, this guy has negative Q, we can actually use the U to find what is the Q number. Use the potential difference to find what is Q. So the next few steps are looking for Q. So firstly, what is U? U is the potential difference between the two rods. What is the potential difference? That is the potential from the surface on the left to the surface on the right. That means if you can find the potential on this surface and the potential on this surface, I mean, not outside, just now we're finding outside, right? Now you find the potential on the surface. So you find the difference that will be your U. This is what this one is trying to say. The surface potential of first rod minus the surface potential of second rod, that will be your U. And of course, you follow this integration. Okay, so anyway, let's move on to see what is this guy. So what is the surface potential of the first one? This is the total potential. And we just know is we said for any position between 0 and D, that's this is our 0, this is our D, between anywhere in between, we follow this one. Now we leave the surface on here, and it's somewhere here. Okay? Somewhere here. This one has the distance of the radius. This radius we know is the R0. So this one has R0. So we need to know, in other words, we need to know in this equation, what is the value of phi at R0. So what we do is we sub x equal to R0. So phi surface 1 will equal to this phi. X equal to R0. And if x is not R0, this ln becomes ln D minus R0 over R0, something like this. Okay? This part is surface 1. This part is surface 2. Okay, and for surface 2. Surface 2 is somewhere on the left hand side of the second. This is the surface 2. And the surface 2 has a coordinate of, the total is D minus R. So 2 is 5x equal to D minus R. Okay. And we find these two from the equation here. Okay, let's skip all the calculations. So in the end, you're going to find that U is something like this. So basically, the question is, remember, we are looking for the potential difference. And this is where all these are going to go. So we have an equation of phi. And we'll say phi for anywhere is the potential. So the difference between these two dots is actually the difference between 2 points. The first point is this point. Second point is this point. And between them, you have a potential drop. This point we call it phi 1, this point we call it phi 2. And just now we have the phi. The phi is the function of x. X is the position. What is the position? So actually, if you have a coordinate system, this is 0, and then this is the D, right? This is D. And so phi 1, you need to know what is the coordinate. The coordinate actually is the radius of the rod. So in this case, the radius is R0. So this is phi 1, R0. And you, from this equation, you sum in x equal to R0 to find it. And what is phi 2? Let's think this way. If this distance is R0, and the total is D, so this one is only D minus R0. Right? So the phi 2, I call it phi 2D minus R0. And also use this equation to find it. Okay. After that, I find the difference, phi 1 minus phi 2. This is my U, which is given. So from this equation, all the way down, I'm here. And from my U is actually something like this. By using phi 1, phi 2, I find this my U. And U happens to be a function of Q, charge Q. And from this one, I find my charge. So if U equals to this one, I find Q. Right? And just now, we will start here. We said, in order to find the E, you need the Q. But finally we have the Q. So now you are going back to give the Q back to equation 2. And in the end, what you find is let's say find the h. Find what is the h. In order to know how to find the h, you need to look at these two rods again. The left-hand rod creates a magnetic field. Right-hand rod. So between these two rods, the magnetic field will go down. So something given by this one, if this one will call it H1, H1 is going down. In other words, it has negative E1 direction, right? Something like this. How about the field given by the second one? If we call it H2, that is also going down. Right-hand rule. So the E2 is also minus E1, right? Okay, now let's find them respectively. Oh, we're going to find H. There is only one or two, and there's only one way to have learned, that is Ampere's law. The H will equal to integration of H will equal to I, right? So the integration is 2 pi r. In this case, what is r? What is the radius? Remember just now we were saying this one will work on x. So suppose you have a position x here, the radius is x. Or I can mark it here. If we are going to find what is the field at x, the radius of course is x, right? H1 the radius of course is x. So integration of this one will be 2 by x. Circumference is 2 by x over circumference, so you have H1. And similarly, you can find H2. H2 is very similar to this one. It's only that I still have a current I. I have 2 pi times my radius. But for H2, given by this one, the radius is between the x and the d, right? So it's d minus x. Radius is d minus x. We have like this, we have H1, H2. In the end, you are going to add them up because they are in the same direction. We don't usually add up vectors, but they are in the same direction. So it's okay, just add them up. You come here, and the total H. Put together the y direction. So the next question is our old friend. He said, what is the Poynting vector? And you have the E here, and we have H just now. So you have E cross H. And the next one, I don't think it will be a question. They're saying, what is the time-dependent energy flux? By saying so, they're actually saying, instead of giving you U, they're saying, instead of just using U, I'm giving you something AC, U sine, and instead of being current, giving you I sine omega t, U sine omega t, I sine omega t. This only means actually you are replacing the U with U sine omega t, replace the I with I sine omega t. That is all. So if you compare this to S and this S, the only difference is U equals to U sine omega t, and I equals to I sine omega t. The rest are the same. You don't need to worry about it. And of course, sine times sine, you have a sine square. So this is why it says this one equals to this S times sine square. Okay, the next question is my favorite actually. You say, what is the mean value of this vector? Means this vector. What is the mean value of this vector? What's the mean value of this vector? Okay, and you have two methods to do so. One is follow this equation. This one can apply to anything that is varying. The mean value is, if you know the period is t, So in 1 hour period, integration from 0 to the period. Okay? So you can, and anything time dependent you can integrate, and then you eventually find is half of S. If that means if the peak value is 1, the mean value is half, something like that. Okay. But this question, I don't like it that way. I don't quite like it that way because actually, if you think this way, integration of S, that is actually we have U and we have I, right? We have U and we have I. So when I look at this one and this one, I begin to think, what is the effective, you know something called the effective DC value. We learned the AC circuit, they said, what is the effective DC value of this one? Never learned something like this? Okay. It's okay. It's only that last time they said if the AC is about, let's say, 220 volt, okay? So the equivalent DC is this value divided by square root of 2. It can't be totally stranger to this. I think you may not remember it well, but should look familiar. So that means the equivalent DC of the U, you divide by square root of 2. Similarly, the equivalent DC of the current is the current divided by square root of 2, right? And since you have the U times I, so it's 1 over square root of 2 times 1 over square root of 2, that is half, right? That means the equivalent DC value you got the 1 over, you got this one. The equivalent DC value you got this one. Multiply together you got 1 over 2. This is my way of solving it, and you can do it if you like to do so. Okay, then the question is I'm going to skip, it's just you summing all the values. They give you some value, you can list them. Nothing. Okay guys, and question 5 actually, question 5 itself looks very scary, but most part I think we covered in the lecture, so I won't use too much time on it. Let's just do it quickly. I think you have the question 5 most part on the lecture. Just quickly read this question. So basically they're saying if the E is conservative and the B is source free, and how to use functions, mathematical functions to describe this word. What is the equivalent? What if I say my E is conservative, basically that is to say rotation is 0. And source free means divergence is 0. Anyway, for something with a source, your divergence is never 0. Because divergence, what is divergence? Is the way how much something converge or diverge, right? Okay? If something has a source, that means a lot of things coming from it. Of course you have a divergence. Only if you have a lot of things that is parallel, you never see them converge, and you never diverge, of course. That is no divergence, right? Source free. So, and next one is this equation. What is Faraday's law? You must know. And the next one, what is the Faraday's law? And so this one and this one is still two equations from the book. What is the scalar of the potential and the vector of the potential? Vector potential and the scalar potential of EM field. And E, they said verify homogeneous Maxwell equation using B. So basically what I'm saying, divergence B has to be 0. Divergence must be 0. Because why? Because B is the rotation of A. That's why I said this field, they have to know. Divergence of the rotation for anything. Divergence in the formula list, right? What is the divergence of rotation, rotation of gradient, something like that. Those things you have that. So just be careful. Just be careful. Okay, and what is this? Next one is saying and prove Faraday's law 2. What is the rotation of P? And why this one is 0? Let's skip this one. Okay, let's look at this guy. G. G actually is the write down G is also again the revision of the theory. So what is the inhomogeneous equation in vector? This guy and this guy, inhomogeneous Maxwell equation. So, but by the way, this is not the original formula. The original formula is the divergence of D, right? That is rho. This is the original thing. Another one is the rotation of H, right? Is J plus epsilon naught e dt. This is the original. But for this one you divide by epsilon. You find it. For this one you multiply mu naught in this case. Then you are going to find that. So E needs to go to B and H will convert to H needs to convert to E needs to go to E, H will convert. Sorry. So you know what I mean? And next. So now we are going to use these two waves. These two waves. They said, what if I sub these two into these two waves? Inhomogeneous. I have the inhomogeneous condition already, and I also have these two. I sub them in. So basically they're saying this is the E, right? And you find the divergence of B. And this is the B, right? Find the rotation of B. How about let's try one? No, we don't. Does anyone don't understand this? This is in your book. I think your book's very nice. So anyway, so how about I just tell you something meaningful? So in the end, find something like this. This is the importance of Gauge condition. Why you need a Gauge condition? Because this Maxwell equation doesn't make sense itself. It just give you a few differential equations and you will never be able to solve them. Why you never be able to solve them? Because these are all partial differentiation. I have one equation and for example dx and dy. How do you find them? But by using the Gauge equation, the Gauge condition, so in the end all the graph theory will convert to something like this. If you look at this one actually is it's very meaningful compared with the Maxwell equation, because although it's the second order, it's only a function of A, right? And this one, second order, but it's only a function of psi, right? So this is why we define the potential vector and the scalar potential, because by that I managed to split those things, and each one will represent only one variable. Because let's say if you look at this one, you only have one variable, so you can solve for A. For this one, you can easily solve for the phi. Okay? So this is what this sentence is trying to say. The partial differential equation is identical, and the advantage is to decouple the differential equation. Okay. And we have one more thing. One more thing is, let's say what this one is saying. If we don't have source, means no rho and no j, no current and no charge, the differential equation will follow these two equations. Okay? And they are saying whether the E and the B follow the similar equations. Basically that means if you cancel this one and change to E, and you cancel this one and change to B, they also equal to 0. What is all this one is asking? You can look at the question later. First, I copy this one and look at the E. And from this one, I have this one. Why? Because the E is from the previous question. Where's my treasures now? If you sum in the E value to here, you're going to find this equation. And look at this one and this one. Okay? Look at these two. And this one actually is this one. It's Gauss condition. This one is Gauss condition is equals to minus rho over epsilon. And this one is another Gauss condition. It's equals to minus mu j. Okay? So why this is 0? Because this is a constant. You are looking for the differentiation of the constant. And you are looking for the differentiation of the actually written out differentiation of the constant. So of course this one, the whole thing is 0. This whole thing is 0. So this must be 0. Using these two. And this is a similar question. And by the guys, and I think since you don't have the question, right? Maybe next time I have to print the question. Yeah. See whether convince them. But yeah, I think it's next week actually the school is open, right? The rest part of the school, the SP is open, right? No food to eat, nothing to eat.
You guys just
Other things are open.